Hello and welcome. Welcome to the subject State Space Approach to Control System Analysis and Design. In this week, the topic of our discussion is design of controllers based on multi-rate sampling. Today's lecture is on fast output sampling controller. The type of controllers which we are discussing now belong to a class of sample data control systems, and in this the inputs and outputs rate of sampling for both is uniform. They are sampled at uniform rates. However, sampling rate for inputs and the sampling rate of outputs are not equal. Both can be different from each other. That is specifically the difference from the regularly sampled control systems. So in the last lecture, we discussed the multi-rate output controller. In this controller, the rate of sampling of the input is 1 by T0. However, the outputs were sampled at a faster rate. N1 by T0, N2 by T0, N3 by T0, etc. The pth output was sampled at the rate Np by T0. N1, N2, N3, etc. These are integers, meaning that the output is sampled at faster rate than the input. And also these integers N1, N2, etc. they need not be equal. They are allowed to be different. So once the samples are collected in one sampling interval T0, then the output signal is computed on the basis of two components. One component is the previous value of the control signal itself, the UKT0, and the other component is dependent on these samples which was collected in just the preceding sampling interval. K times some gain times the values of outputs at that finer intervals collected during one input sampling interval. And this kind of a controller is, of course, a dynamic controller. Now, condition for almost satisfactory or full pole placement was that each of these integers N1, N2, etc. be larger than the respective these observabilities. N1 is greater than nu1, the observability index of output 1. N2 greater than equal to nu2, the observability index of output 2, and so on. For pth output, Np should be greater than or equal to nu p, the observability index of system with pth output. Now we will be discussing the fast output sampling controller. In this controller, essentially, these inputs and outputs are sampled at different rates as was done in multi-rate output controller. However, there are two differences from the multi-rate output controller. The first difference is that all the outputs are sampled at the same rate. That means N1, N2, etc., Np all are equal, and they are equal to integer n. Second difference is that in the fast output sampling control, the controller is non-dynamic. It depends only on the values of the samples of output collected during one sampling interval. This is the schematic shown here. I'm sorry, this is supposed to be KT0, this not T1, this is a misprint. So the input, this side switch is closed at the regular intervals of T0, and this side the switch is closed at regular intervals of n by T0, or the sampling period this side is T0 by n. So smaller compared to T0. And this n is of course chosen depending upon the type of design we want. We will see about it. Now, in order to see how a fast output sampling controller looks, we again begin from this set of equations, state and output equations for nth order continuous time linear time invariant system, which has m inputs and p outputs. So we are considering this general linear time invariant system of order n with m inputs and p outputs. Now we assume that the input side, the sampling period is t, capital T, and the output side sampling period is delta, which is t divided by n being an integer. So basically in the fast output sampling, the outputs are to be sampled at a faster rate than the input. Now we list down the dynamic equations for the discrete time system corresponding to these two rates, the rate of sampling 1 by t and the rate of sampling 1 by delta. So the discrete time system, for the system sampling rate as 1 by t is this. It is characterized by the matrices phi t and gamma t, and phi t is e power 8t and gamma t is integral e power a tau v d tau between 0 to t. This relation we discussed in the first lecture of this week. These relations we discussed. Similarly, if the system is sampled at the rate 1 by delta, again the system is characterized in a similar manner, only the system matrix and the corresponding input matrix are different. Now the system matrix is phi delta, which is e power a delta, and of course gamma delta will be e power a delta, e power a tau v d tau. Integration limits will be from 0 to delta in this case. So we have the same continuous time system sampled at two different rates, 1 by t and 1 by delta. We have two different descriptions. This is our starting point from which we will derive basically the equations for the fast output sampling controller. Now in this case, the control signal is generated according to this control law. Ut is a boldface L, which is set of L0, L1, L2, etc., Ln minus 1. N minus 1 gains, N gains, N gain matrices in case of multi-input, multi-output systems, multiplied by these samples of output collected in one sampling interval t at the regular spaced intervals of delta, subintervals delta. So this is y k minus 1 t plus delta, the output at k minus 1 t plus 2 delta, and so on. So this is the sampling rate t, 2t, etc. for the input, and in that we consider kt and k plus 1t, kt and k plus 1 t, these two instants. So input is updated at these two instants. However, the output signal is collected several times in this interval, and these sub intervals, each of them has a measure of delta. So this is kt plus delta, this is kt plus 2 delta, this is kt plus 3 delta, etc. And this is kt plus n delta or k plus 1 delta, because t is n delta. So the samples of output collected here, this is y k minus 1 t plus delta. And similarly, the samples of output collected at the next time interval is this one, and so on. So these samples are collected. These are multiplied by this gain matrix boldface L, and we get the control signal to be applied at k plus 1 t or kt. So this is how the control signal is generated in case of fast output sampling feedback controller. Now, of course, this n is to be selected and L, that boldface L, has to be designed. So we evolve the equations using which we can design L, and for that we need to know a state feedback F. So by using any of the various well-known methods, we design first a state feedback gain F, such that this phi tau plus gamma tau F, phi t plus gamma t F, this t is phi t, gamma t are the matrices characterizing the continuous time system sampled at the rate t, capital T. So for the system sampled at capital T with sampling period capital T, which is given by phi t, gamma t, we design a gain F, state feedback gain F, such that this closed loop system is stable and as well as it has desired pole locations. Of course, there is one compromise. It is not permitted, we will see why, it is not permitted to have any pole at the origin. So phi tau plus gamma tau F can have poles anywhere except at the origin, so that the system has desired performance characteristics, of course with the restriction that poles are not permitted to be the origin of the Z plane. So we design an F. This is the first task to be done, and we will derive this relation. The fast output sampling controller gain L, which realizes this F, is given by this relationship. Bold L, boldface C, this product should be equal to F. And in this, if a L is obtained, then F will be realized. C is known. C is given here. C is boldface C0 plus boldface D into F, this whole matrix, multiplying the closed loop system matrix inverse. So this is why the poles of the closed loop system is not permitted to be at the origin, because in that case we will not be able to generate this inverse. So this boldface C matrix is defined by this relation. This is product of two matrices, and of course C0 and D are also known. They are given here. C0 is C into phi delta. Phi delta, please remember, phi delta is the state transition matrix or the system matrix for the continuous time system sampled at the rate 1 by delta. So phi delta and gamma delta are matrices characterizing that sample data system in which the sampling rate is 1 by delta. So C0 is given by this relation. C is the output matrix, phi delta is the system matrix. So C into phi delta, C into phi delta square, and so on. C into phi delta power n. And D is C gamma delta. Again, C is output matrix and gamma delta is the input matrix for the sampled system at the rate 1 by delta. So C gamma delta. Then next one is C phi delta gamma delta plus C gamma delta. Next one will be C phi delta square gamma delta plus C phi delta gamma delta plus C gamma delta. So in this manner, first one is C gamma delta, second one is C gamma delta plus C phi delta gamma delta, third one is these two plus C phi delta square gamma delta, and last one is etc. C phi delta power n minus 1 gamma delta. This is expressed concisely by this. So this is how C0 and D are, and C0 and D are known, F is designed. So we know this as well as this, and so we know C, and so we can solve for L. So if this LC is equal to F, this solution, the condition is that number of sub-intervals in T should be greater than or equal to nu, the observability index of the system. This system, the system sampled at the rate delta, 1 by delta. And what is the observability index? Just to recall, this is the largest value of nu for which this matrix C phi delta etc. C phi delta nu minus 1, this matrix and the next matrix C phi delta square etc. C phi delta nu. So the largest value of nu for which this matrix will have the same rank is the observability index. And if n is chosen to be greater than or equal to the observability index, then the solution of LC equal to F exists. L can be solved. This is the condition. So essentially we have to set up the matrices C, the matrix C, which is set up using C0 and D, and then if we have chosen n satisfying this condition, then L will exist. And LC realizes this state feedback gain F, and so the response of the closed loop system with this fast output sampling gain controller will be identical to the response of the closed loop system with the state feedback system, U equal to Fx, that controller. So now we derive that relation. How we got that relation? The derivation follows in this and next few slides. So we have the system sampled at the rate phi delta gamma delta. For this, the state at the one sub interval after the sampling interval t, kt, x kt plus delta. So this is kt, this is here kt, and we are considering the value of x here, kt plus delta at that time. So at that time x is given by phi delta x kt, this is the value of x here, plus gamma delta u kt, the input which was applied here. Now x kt plus 2 delta will be phi delta at this previous instant. So if we consider here the state, it will be state transition matrix into the state here. So phi delta x kt plus delta plus gamma delta u kt. Now because input is constant throughout, in the large subinterval t the input is constant, so that is why we are using u kt. And here we substitute in place of this expression which is written here. And then we simplify, so we get x kt plus 2 delta equal to phi delta square x kt plus phi delta gamma delta plus gamma delta whole thing multiplying u kt. Similarly, we can obtain x kt plus 3 delta and so on, and at the end x kt plus n delta, which will be given by this phi delta power n x kt, the value of x at the end of the interval kt, pre-multiplied by phi delta power n, plus this phi delta power n minus 1 gamma delta plus phi delta n minus 2 gamma delta and so on, plus phi delta gamma delta plus gamma delta, this whole thing multiplying u kt. So that gives x kt plus n delta, the x at the end of the next subinterval, x kt plus n delta, or x k plus 1 t. This is x k plus 1 t because n delta is t. So we get x. Now next, because output is c times x, so y kt plus delta is c times x kt, this one, x kt plus delta. If this is multiplied by c, we will get y at x kt plus delta. So that is what x kt plus delta is c times x kt, which gives this. Similarly, y kt plus 2 delta will be given by c times x kt plus 2 delta, and because that is equal to this one, we substitute this. So we get y kt plus 2 delta as c phi delta square x kt plus c phi delta gamma delta plus gamma delta into u kt. And in this manner, we finally evaluate y kt plus n delta given by this one. It is simple. So once first we obtain the values of state at different end of subintervals kt plus delta, kt plus 2 delta, etc. Output is C multiplying the value of states, the output matrix multiplied by the value of states, and so we get these. And if we collect them together, this is the boldface y, which is k plus 1, y k plus 1 t will be, this is concise form of representing this side. The values of this boldface C0 and D will be next. So this is equal to C0 x kt plus du kt, and C0 will follow from here. And of course, before we do that, we substitute in place of u kt f x kt, and so this becomes C0 x kt plus d into f x kt, and when we take x kt common on the right, then we are left with yk plus 1 t equal to C0 plus df. And we see here that C0 I'm sorry. So this C0 is C phi delta etc. This was given in one of the previous slide, and D will be this C gamma delta etc. That was also given in the previous slide. So we proceed further. The input ut between this interval just after kt, to k plus 1 t. In this interval, the input is given by this boldface L into that stack of outputs collected during interval here. This is where ykt was corrected. This boldface y. That multiplying L is the input to be applied here just after kt to k plus 1 t. That is ut. So in place of ut we have L, and this ykt we just derived here. Ykt, because yk plus 1 t is given by this, so we have ykt given by this into x at previous time instance. So that is substituted here. And we get u during that interval just after kt plus 2 k plus 1 t. We get that input during that interval. And we just, because during the entire interval the input is constant, so we substitute t equal to kt, and so ukt is given by this expression, so essentially this one. And that means that xk plus 1 t will be sorry, it is not will be, it is with the state feedback. This is the system, phi tau plus gamma tau f xkt. This is with the state feedback, and this is ukt. So xkt we solve from here. Xkt pre-multiplying by inverse of this both sides, xkt is obtained in terms of xk plus 1 t as this. And this one means xk minus 1 t will be a similar inverse and xkt. And this whole thing we can substitute here in place of xk minus 1 t. And that will give ukt equal to this. This whole thing into this whole thing, which is this. And this whole thing we are denoting by that bold C, boldface C. So thus we got U equal to LC, and now we substitute, because this is the closed loop system. So in place of ukt we substitute this relation, and we get phi tau xkt plus gamma tau L, this whole thing in place of ukt into xt. So this ukt into xt we substituted by this one, which was derived here in the previous slide. This is substituted, and that gives the closed loop system. Phi tau xkt plus this, so closed loop system is phi tau plus this whole matrix into xkt. And here we denoted this thing as C. So that boldface C, this whole thing. So we have phi tau plus gamma tau LC xkt equal to xk plus 1 t. This relationship we obtain. And of course, this is also comparable. This is that one, this phi tau plus gamma tau f xkt, and that means LC and f should be S. This is what we obtain, LC equal to f. Now the condition for existence of L, solution to L, is that C inverse should exist. So we will have L equal to f into C inverse. this boldface L, this is boldface C. So C inverse should exist, and because C inverse itself was expressed in terms of product of C0 plus DF and phi tau plus, so this C, bold C was C0 plus boldface DF into phi T plus gamma T F inverse. So if we have to have inverse of C possible, then this inverse and this, both these inverses should exist, and that is written here. Both should be invertible. That is one. Other thing is, so for these two should happen if n is greater than the observability index of the system. Number of sub-intervals into one input sampling interval should be greater than the observability index. And it was stated earlier, but we recall that there should be no pole at the origin for this closed loop system matrix. So F is designed to satisfy the transient response specifications, etc., or to have the closed loop pole locations except at any pole at the origin. It should have anywhere else but not at the origin. That is the restriction. So if number of sub intervals during one input sample interval is greater than the observability index of the system, and if the closed loop system matrix F, closed loop system matrix with the state feedback gain F has no poles at the origin, then C inverse will exist, and then LC equal to F, that equation can be solved. We consider one example. We take this second order system, continuous time second order system, 0, 0.5, minus 1, 0. This is the A matrix and this is the B matrix. Of course, this is a scalar system. This is C matrix. So N is 2, M is 1 and P is also 1. So if this system is sampled for a sampling period of 1 second, then this will be the phi t and gamma t characterizing the discrete time system corresponding to this continuous time system sampled at the rate every 1 second. And for this one, we can design some state feedback gain to obtain these pole locations, and we will have this F. This F will obtain this closed loop pole locations for this system, giving underdamped response. Now once F is obtained, then next the discrete time system for that continuous time system for the sampling at the rate delta, which is T by N, and N we are choosing 2 first. So delta is half, and for that this is the system matrix for the corresponding discrete time system, and this is the input matrix, phi delta and gamma delta. And from that we obtain this as bold face C0 and this as D, and we combine C0 plus DF into phi t plus gamma TF inverse, we get this. And then LC equal to F, so LC equal to F, so L equal to, here this C is invertible, so L equal to F C inverse, and we get this. This will realize the same control characteristics as that obtained with the state feedback gain F, and thus we obtained the gains for the fast output sampling based controller for this the continuous time second order system with one input and one output. We can do several other examples, but this essentially brings out how one designs a fast output sampling controller. Of course, we could have chosen a different n, larger n, 3 or 4. Accordingly, we have to calculate phi delta, gamma delta, C0D, and then C, and again solve for L. In that case, we'll have to choose a few elements of L freely or based on some other considerations, because there will be fewer equations than the number of unknowns, that gives a little design freedom that can be done. So we try to summarize what we learned in this video, the fast output sampling controller. Now, the feature of the fast output sampling based controller is that the samples of output are collected several times during one sampling interval of the input. And the input is computed using these samples of output collected here at the end of that previous sampling period, and then the controller is applied. The control signal is applied at the end of the sampling interval. And almost any state feedback can be realized in FOS. Of course, there is only one restriction, that there should not be any pole at the origin. So subject to that restriction, any state feedback can be realized, and that is the reason this almost is written here. And then, of course, observer is not required. We discussed in the introduction in the previous videos that if we have to implement a state feedback, that necessitates one observer, and we learnt about the Leuenberger full order or reduced order observer. But like MRIC, the multi-rate output controller obviates the need of an observer. Similarly, based on fast output sampling based controller, we will not require any observer. There is one small problem, that first the samples of output are to be collected, and then only the input will be calculated here at the end of this subinterval. So between 0 to t, the control signal is not possible. Control signal will be possible subsequent to t. So between 0 to t, a control signal has to be assumed. The input has to be assumed. That is the another limitation besides this one. No pole is permitted to be at the origin of the Z plane. Similarly, in the first sampling interval, the system input has to be assumed, or it can be assumed 0, so that system will behave autonomous in this period. That should be tolerable. Then this controller can realize any state feedback, and observer will not be required. So in that way it is simpler. So with that we come to end of this video. Thank you very much, and see you again in our next lecture.